underground cavities, the development and documentation of several machine learning software, including NetVisa, used at the IDC, and BetaZ, used in the oil and gas industry. She's currently involved with applying machine learning to the field of finance. She will be the moderator for this panel and will introduce the other panel members. The floor is yours, Heidi.
Thank you, Ronan. So it's my pleasure to introduce a very distinguished set of panel members for this where I think will be a very interesting discussion. We have with us today Dr. Kardi Teknomo, who is Professor of Civil Engineering Science and Applications at Petra Christian University in Indonesia. He self-describes himself as an amalgamation of civil transportation, traffic engineer, and an information scientist by education. He's a founder of Revolve-LDO. He's an international consultant for the International Finance Corporation of the World Bank. He's worked for Toyota. He's worked Savannah Solutions in Switzerland, Probe Software in the USA, and Aramis in Brazil. He's been an associate professor at the University of the Philippines, at the University of Wisconsin, and the Austrian Institute of Technology here in Austria. He has dozens of awards, dozens of scholarships and publications in the field of AI, particularly in traffic, transportation, and the most wonderful word, pedestrianology. And so one of the things I really liked about his resume is that he self-proclaims himself as enjoying life and still learning to be better. We also have Professor Tingawende Basad. He's chief scientist with the S&T program at the University of Luxembourg. So that's not the S&T that we're currently attending now. It's an interdisciplinary center for security, reliability, and trust. And it helps collaborate public, university, and private projects. He's worked with the Luxembourg Stock Exchange, the University of Pierre and Marie Curie in Paris, and at UC Santa Barbara. Again, he's also published dozens of papers. His particular expertise is in self-repairing and self-debugging computer code. We have also with us Professor Stuart Russell, who'll be giving our keynote speech. He's a professor of computer science and the Michael H. Smith and Lofty A. Zeta chair at the Berkeley School of Engineering, CS division at the University of California at Berkeley. Again, another long list of awards and publications. And in fact, on his CV, his job resume goes back to 1978 when he was a programmer for IBM Systems and Engineering in the UK. So long history. He's published several books, including the book, Artificial Intelligence, A Modern Approach, which he published with Peter Norvig, which is one of the most, basically the seminal text on AI. And he's also worked on a number of popular articles. You occasionally read of him in the popular press, including one that I really love the title of, which is Transcendence. An AI researcher enjoys watching his own execution. And finally, we have with us Dmitry Kuznoff, who gave the keynote speech on Monday. He's a physicist and a mathematician. He's the Deputy Undersecretary for AI and Technology for the Department of Energy. He's also a visiting researcher at Yale. He's a real physicist. His PhD was in theoretical nuclear physics. He's published over 100 articles in a book and also gave a very interesting speech on Monday, which I hope we'll be able to discuss in this session here. So with that introduction, let's go ahead and Stuart, maybe you can share your screen and give us our introduction, and then we'll summarize a little bit of what Dmitry talked about on Monday, and let's talk about it. I look forward to a very enlightening, intelligent, and interesting discussion. So Stuart, you have to push the little button to share your screen. And you also have to unmute yourself. So the mute thing, there you go. You're still muted.
Okay, thank you very much,
There
Heidi. And I'm delighted to present a whirlwind tour of AI and what we've been doing with AI within CTBTO. So first of all, AI is about building machines, and the standard definition of what counts as an intelligent machine is a machine whose actions can be expected to achieve its objectives. So if you want a canonical example, you could take the self-driving car. It receives percepts from its environment through its sensors, cameras, lidars, and so on. It uses its effectors to produce actions. So the effectors will be the steering wheel, the accelerator pedal, the brake, maybe the horn. Those actions in turn affect the environment, which then affects subsequent percepts. And to make an agent, it also needs some objectives. And traditionally, those are provided directly by us, by humans, who tell the car where to go. And we also supply objectives like don't kill pedestrians and get there quickly and so on. So this has been going on for 70 years or so. And we're still trying to figure out how to make it work. So the job of the AI community is to fill in this box in the middle with software that actually does the right actions given all the percepts and the objectives. Now, if you read the newspapers or watch television, you will get a very different impression of AI. You would think that AI is all about moving towards the next flashy demo, whether it's DeepMind beating Kasparov or Watson winning Jeopardy or AlphaGo defeating Lee Sedol. These are really, as I said, these are demos. These do not represent breakthroughs. They are simply demonstrations of capabilities built on breakthroughs that may have occurred decades earlier. It's also not about creating conscious machines. So most movies involve AI becoming conscious by some spooky emergent process. And we actually have absolutely no idea about consciousness whatsoever, and nobody really works on it. So this has nothing to do with AI as a research field. Also, there's often a confusion between AI and machine learning. Some people will tell you that AI has been replaced by machine learning, which is sort of like saying that a car has been replaced by its steering wheel. It just doesn't make any sense as an assertion because machine learning is a subfield of AI, and it just means any method for improving the performance of an AI system through experience. And many AI systems don't learn at all. For example, Deep Blue didn't do any learning. It was built by writing C++ code and improving it through manual methods. And then that was enough to beat the world champion. It's also the case that machine learning is not about neural networks, which the media will often tell you that machine learning was invented in 2012 and it involves training enormous neural networks. This is the case. You can apply machine learning to any kind of AI system. It could be a system based on logical knowledge or probability models. Parametric circuits is another name for neural networks. But you can even apply machine learning directly to C++ programs, although it's quite difficult to do that. And now within machine learning, we often distinguish between model-based methods and model-free or sometimes black box methods. And roughly this distinction is about the extent to which you can understand the system as being based on identifiable knowledge. So the word model here is referring to some knowledge about the world that the system might possess or might acquire in some explicit form. So I'm going to talk a little bit about one particular model-based approach, which is the what we call the Bayesian approach. And in Bayesian approaches, we are building probability models that represent our knowledge of the world. And then we might refine or update those probability models with data. We typically divide the model into two parts. The first part, the generative prior, says what we think the world might be like. And then the second part we'll call the sensor model. That says, given what the world is, what would we expect the observations to be? And if you take those two models, you can basically do everything. You estimate the parameter of those models typically from historical data that you've collected. And then you do Bayesian inference. So just apply Bayes' rule to compute the probability distribution over what the world is, given the observations that you've seen. And so that's it. Right? That's how we build data analysis systems in the Bayesian approach. So you might ask, well, how on earth do you represent these models? What do you mean a generative prior over what the world could be like? Right? What does that actually mean? So you need a formal language to write down these probability models. And since the late 1990s in AI, we've been developing something called Parabolistic Programming, which is a way of taking the universal expressive power that comes from Turing machines and combining it with probability theory. And we can do this in one of two ways. One thread basically combines probability with programming languages, and another thread combines probability with first-order logic. But in either approach, we gain enormous expressive power that lets us write down very complex probability models. So for example, if I want to write the rules of Go in a probabilistic programming language, that might take about a page. In other words, about the same as it would take to write them down in English. If you try to write them down as a circuit, whether that would be a Boolean circuit or a neural network, it would be about 1 million pages. And so having this kind of expressive power is extremely important for model-based systems, but also for machine learning, because learning a system that has a 1 million-page description requires billions or possibly trillions of data points. So with these languages, we can represent any computable probability model, and we can do general purpose inference, namely a single general inference algorithm can handle any model, any data, and any query. There's no guarantee on how fast it's going to run, but in principle, we have full generality. And this allows you then to combine prior knowledge and data in a cumulative way. So this is the standard model-free machine learning system. Data comes in and supposedly knowledge comes out. With probabilistic programming, you can also supply prior knowledge, and that constrains and generates the hypothesis space. And then the knowledge that you learn can be fed back in so that you get this process of cumulative learning that's so characteristic of human beings. And the field has been growing very rapidly over the last decade or so. One might even say growing exponentially, up to 2,500 papers published in 2020. So how does that work for CTBT? So in CTBT, we have the IMS, which collects data from all the sensors, mostly seismic data. And then from all that data, we produce a daily bulletin. So how do you formulate that in the Bayesian way? Well, the evidence, the observations, are the waveforms that we collect from all the seismic stations. The query is what happened? And the model contains what we know about the geophysics of the world and seismology. The natural seismicity, the man-made, by treaty, uniform seismicity for man-made events, the phases that seismic events produce, their travel time, the way they're attenuated, and then detection probabilities and noise thresholds and so on. And so that's what the model is. This is the original NetVisa model that we wrote back in 2009, I think. And so that's the basic network processing system that NetVisa carries out. And as I said, there is no algorithm. There's the model, there's the data, and then there's effectively general purpose inference. I'm not going to go through this step by step, but I'll just show you a couple of pieces. So inside that model, there's a depth location prior for natural seismicity. This is the depth location prior between 300 and 500 kilometers deep. and this shows where we expect to see seismic events at that depth. This is part of the travel time models. This is travel time residual for Station 6, which I think is Alice Springs, and we're showing a nice Laplacian residual curve. And when you do inference on this type of model, you automatically get multilateration. You automatically get noise rejection. You're able to rank the competing hypotheses about possible associations between arrivals. And we also handle negative evidence. So if a station doesn't show an arrival, then that affects what hypotheses are formed and what probabilities they have. And the system works pretty well. You can see the results in Ronan's paper that appeared in Page Off last year. And here's a nice pretty picture. This is the 2013 DPRK event showing the real-time net visa location, which actually turned out to be much closer to the tunnel entrance than the LEB location, which was produced after a big huddle of geophysicists looked at all the data. So I want to talk about just one improvement on NetVisa. So we can think of NetVisa as a generative model that models the production of detections from events. And those detections are the output of the station processing. And then from that data, the inference process goes in the other direction, inverting the model to infer events from detections. The SIG-Visa model actually goes all the way from events to waveform signals. And in the process, it adds a lot more physics. So it adds models of general waveform shape, of coda decays. It allows for superposition of signals from multiple overlapping arrivals. It implements spatial continuity of travel time residual, so you automatically get a kind of Kriging effect. And most importantly, spatial continuity and repeatability of waveforms. So you get waveform matching for free. Right? So when you run inference on the SIG-Visa model, then you automatically get nice things like sub-threshold detection. So the signal can be way below the noise level and still be detected. You get global beamforming from all stations simultaneously. You can get a good location often from a single station detection if the waveform matches some historical event. You get double differencing for free and deconvolution of overlapping arrivals. So all these things just fall out from doing inference on a model that contains more of the physics. And we ran this on a year's worth of data from the Western US when the array was moving across the US. And I'm not going to go into this in great detail, but if you look at, for example, this is the recall, so what percentage of events were detected between, let's say, the magnitudes 2 and 2.5, you can see that we get more than twice as many events as LEB using exactly the same data. And then between 1 and 2, we actually get about 10 times as many events as were found in the LEB. So I think if we were to scale up SIG-Visa to full-scale global monitoring, we might effectively get a 1 magnitude reduction in the detection threshold. So I think that would be a big deal. So looking forward, I would say human oversight and analysis is still really important because the model can only handle things that are modeled. We don't, for example, have models of what happens if a meteorite hits the ocean. So you would get a bunch of detections from the hydrophones, but you probably wouldn't know how to deal with them. And so we would probably need some human oversight to handle that. We only have 14 phases in the model, and other phases could sometimes be useful, and we wouldn't know how to do that. You have to allow for the possibility that there can be picking errors in the station processing, and those would have to be fixed. We don't assume in NetVisa that the arrival times are correct, so we allow for pick errors, but sometimes to actually unpick and do everything correctly, you need some human oversight. Now, I think there are many things we could do in addition to going from NetVisa to SIG-Visa modeling. rather than producing a deterministic bulletin that just says, okay, here are the events. I think we ought to flag the fact that sometimes there is real residual uncertainty about what happened, and you should output multiple hypotheses with their probabilities and allow the analyst to explore those and try and figure out which ones are right. At the moment, our models are fixed, so we train them on a batch of data, and then we fix them, and then we use them for a while. But in principle, a good Bayesian would say you should be constantly re-estimating your models as you go along for every single piece of data you collect. And also in the models, we've assumed that the catalog locations are correct. In fact, of course, as you know, the catalog events locations are wrong. We should treat all of those as latent variables. And so in some sense, do a global, all the way across time, global relocation using Bayesian inference. And finally, it's worth mentioning that when you flag an event, this is really a decision, right? A decision in the sense that it has costs and benefits. And you need to look at the relative costs of false positives and false negatives to decide sort of what is your threshold for declaring an event and for flagging it for further investigation. And if you can write down what those relative costs are, you can derive the probability thresholds. In the model, we just set those probability thresholds so that we get some reasonable looking behavior. And you can see I've marked the two relevant pieces in red. So we say that 99.9% of events are natural, which is an underestimate. And it's an underestimate because that way we are accounting for the fact that a false negative is much more costly than a false positive. And then, of course, if an event isn't natural, then we assume that it comes from a uniform prior over the entire Earth. And of course, if you had suspicions, you might want to have a non-uniform prior to get more focused monitoring. Okay, I'll just spend a couple of minutes going a little further into the future, as Ronan asked me to do, just to perhaps stimulate some debate. I think in the next few years, we will probably see, I would say the last decade was clearly the decade of deep learning. But I think in the next decade, we may see the pendulum swing back as deep learning kind of plateaus in its capabilities. And we realize that, in fact, we need symbolic methods as well. And perhaps we'll find some nice hybrid of the two. I think, again, the last decade, you could say, was the decade when visual perception and speech perception really made enormous progress. I think this decade we'll see huge progress in language understanding, and that will make huge inroads in commercial applications of AI, both in industry and for personal applications, which could have very significant impacts on employment of human beings. Beyond that, it's extremely hard to predict what's going to happen. So I don't believe that bigger data and bigger machines will solve the AI problem by any means. It requires conceptual breakthroughs that are very hard to predict. And just to show you how hard these things are to predict, here's a speech from Lord Rutherford, the famous nuclear physicist, in 1933, September 11th, by coincidence. And he was asked whether it might be possible to unlock the power of the atom. They knew what the power of the atom was, they had no idea how to get at it. And he basically said, it's complete nonsense. Anyone who looks for a source of power in the transformation of the atoms is talking moonshine. And he said this in many ways on many different speeches. The following morning, Leo Szilard invented the neutron-induced nuclear chain reaction. So it went from never to basically, at least conceptually, solved in less than 24 hours. So I do not want to make any quantitative predictions about the future progress of artificial intelligence. Here's someone who you might be familiar with. This is Alan Turing. He's the founder of computer science, in many ways the founder of AI as well. And here's what he had to say. It seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. Was he right? Well, I actually don't think he was, but I don't have time to tell you why he's wrong. So to summarize, Bayesian model-based approaches allow a principal combination of knowledge and data. And I think for anyone in geophysics, we know a lot about the Earth. We know the Earth is big and round and three-dimensional. And we know that there is time and space and velocity. And if you don't know those things, it's very hard to understand the data that comes out of the IMS. We can put all that knowledge into our machine learning models using parabolistic programming, and we can get good results as a consequence. And NetVisa, I think, shows that the approach is viable, but I think the SIGVisa approach could give us a lot more in the way of detection sensitivity, location accuracy, and so on. And just to stir the pot, I will say AI systems will eventually surpass human abilities across the board. I'm not going to say when or how, but I'm pretty confident that they will. If you want to know how not to destroy the world, I wrote a book about it called Human Compatible. That's it. Shameless plug. Thank you very much.
Thank you, Stuart. That was very interesting, and I've been jotting down on my piece of paper here many questions to ask you, particularly philosophical questions. But before we do that, let's give the other panelists a chance to speak. So Tekawende, would you like to go first and tell us a little bit about what you've been working on and what your philosophy is? And in order to do that, you're going to have to unmute yourself, but I'm going to mute myself so we don't get feedback.
Yes. So thank you very much. I'm not sure. Can you see my slides now?
Yes, we can see your slide.
Okay. Yeah. Okay. Good. So I'm Tekawende Bisiende. So I'm from the University of Luxembourg, and mostly I work on software, software engineering for repairing software in terms of vulnerabilities, in terms of bugs, and I do all of this with a lot of AI. And since it's AI software and repairing software, we also have a lot of industry applications with in fintech, regtech, code management that are related to AI. So today, what I want to discuss is a bit one thing that the previous speaker already mentioned when he talked about interpretability and basically some kind of trade-off. There is a trade-off between having a very accurate model and an interpretable model. So one of the things, one of the problems with AI, at least, the recent evolution of AI, when we talk about deep learning, for example, is that, most of the algorithms are a bit black box, okay? The inner workings of how the model actually made a decision given the inputs is not readily interpretable. And this is what the previous speaker mentioned when he said that, giving the decision alone is not enough. You need to give extra information and give a chance to the analyst to actually, know how to triage further. Okay, because it's just a probability of, for example, of the events that were discussed there. So there is a trade-off to be made when we look at the different algorithms that are known. Today we talk about, of AI is being extremely powerful. So this is mostly the neural nets, and they are very accurate indeed, but they are the less explainable models that exist. But we have less, I would say, less sophisticated models, such as like if you have classification rules about how to store products in a shop, for example, and these are not so accurate, but at least it's very explainable. We know why we get these results every time. So why do we need to have explainable models? Actually, there are many good reasons. There are legal reasons today, that force people to actually try to get explainable models. There are also practical reasons. When we are not so confident, or when we need an analyst to actually go further, or go behind the model and try to do some tasks to actually confirm. So you cannot just give the prediction, you also need to give further information. There are also ethical questions related to that. And last, there are also prudential questions. So if I take, for example, the case of the general data protection that the EU has made, and this one, the GDPR will effectively create a right to explanation, because a user can ask for an explanation of an algorithmic decision for that was made about them. And that's important. If you look at the articles 13 and 14, they clearly state that when profiling takes place, a data subject has the right to meaningful information about the logic that was involved. So this means that if we use very sophisticated AI models, for example, in the realm of fintech, to make a prediction, like to refuse an overdraft to someone, or to refuse a loan, this client, this consumer may ask, an explanation. And this is where it becomes complicated. Because then, if the AI model did not give any explicit information, we need to do what? We may, the analyst or the banker might be required to fake it. And this is very dangerous. Okay. In complex tasks, in the industries will favor transparent and interpretable models, even if they have lower accuracy. And I guess this would be the case, for example, in nuclear, in nuclear systems and so on, because you better be able to explain what's going on rather than be able to say that, I have 99% of precision, but what about the 1%, which can happen? Okay, so this is a case, for example, of a fintech partner that we are working with, and here everything is actually how to say, constrained, by the regulatory environment, by the different audiences that he must cater. So there are clients, there are analysts, regulators, managers, and the AI systems, when it gets in, must really give information so that all of these people might understand what's going on. So basically, what is explainability? Okay, so there are obviously many different ways of putting it, okay, but in our case, we are going to say that explainability is going to be used interchangeably with interpretability. Okay, we aim to respond to the opacity of the inner workings of the model while maintaining the learning performance. This will give machine learning models the ability to explain or to present their behaviors in understandable terms to humans. Okay, so we have different types of explainability, of course. There is the local explainability, meaning that for every decision, we might be able to say why this decision was made. What were the features that were used to make this decision? And then there is what we call the global explainability, meaning that how does the model itself behave, when we look at across all the features. And on the other side, we can also have the inherent, explainability and the post hoc explainability. Those that come, that require another framework to generate the explanation after a first framework has actually built the model. So this is also very important in the way that we want to integrate explainability in an industry, in a production pipeline. Okay, so here, if you want to have global explanations are going to actually increase the model transparency. So what is that going to do? It's going to increase the trust in the model. Okay. However, local explanation are going to uncover the mapping for a specific prediction. And what is this? This is going to increase trust in a given prediction. So generally, the local explanation, the local explanation is a concern for the clients, okay? And the global explanation would be a concern for whom? It will be a concern for the guy who is implementing it, the developer, and so on. So all I was trying to say, yes, thank you. All I was trying to say here is that we are trying to do explainability.
Let's keep on our schedule.
Yes, yes. We are trying to do explainability, and explainability is mostly, about bringing, trust in the model better, because precision in a small data set doesn't mean that the AI is working so much. So thank you very much, and I look forward to the discussion. And I liked the opening that the previous speaker gave about whether Alan Turing was right when he said that AI is going to to overpower us. Thank you.
Thank you so much. So now I've proven myself to be a disciplinarian moderator. Cardi, it's your turn. I know you had a 9-minute discussion that you cut down to 5. Cardi, oh, there you go. See, we had this technology so perfectly. You'll need to unmute yourself.
You need to unmute yourself, Cardi, and
it's the little green button at the bottom.
It is.
There you go.
Okay, let's start.
Okay.
Okay, I will come. Okay.
Hi, Cardi. You're coming in with much distortion. I think your speaker might be too far away from your...
Okay.
There you go.
Okay. Then I will just share this if this is a problem. Can you see it?
You're sharing. You're sharing properly.
Oh, okay.
you might want to expand your screen to the
Yeah, okay.
presentation mode.
Can I share this?
There you go.
If you do a presentation
Double
mode.
thumbs up.
Okay, thank you. All right. So, in human versus machine, okay, I would like to ask about this is the overview. What is the pros and cons of human analysis versus automated machine method, and what we have been achieved so far, and what are the challenges, and what are the prospects for the future, and what is it for CTBTO? Between man versus machine. So which one is more superior in what sense? If we say that we are better in terms of thinking, okay? So what is the definition of thinking? Is computing considered as thinking? Is memorizing considered as thinking? Or is it the problem solving that considered as thinking? What if the machine can do all of this cognitive skill and also creativity? Okay, so then we will have a problem because now the machine will be actually much better than us as a human being. Historically, for example, computer was the job of humans, and now is a machine, right? Driver is right now still a job of human, but probably in the future it will become the job of machine. So the challenge is we keep increasing our barrier to intelligence by keep demanding higher capability of the machine itself. And we keep changing our definition of what is thinking. So is creativity considered as thinking? What if the machine can actually produce better poem, better song, better picture, or better movie than human? Will we consider that machine can think too? And most people that are not familiar with machine learning, for example, thinking that, well, that's programming, okay? We as human is the one who program it. But this is the old paradigm, because when we say programming is kind of algorithm step-by-step instruction, and we put the human knowledge into the program's rule. But with the advance of machine learning, okay, what we have is actually not the program itself. Okay? What we have is the program, that kind of black box or glass box that is very capable to do their own programming on itself. So what we need to have is only the data that we fit into the black box or the glass box here, and then the machine learning will create the internal rule for itself. So one of the machine learning method that I developed is called ideal flow network. So in this case, it's a glass box method, okay, that also can inversely generate the random input data. Okay. Now, I'll demonstrate in the example here. Can you see my screen? Okay, so this is just an example of a website that I created. So this is a Mozart music that we put inside, and we can generate based on IFN. Okay. And you see that the music generated is very similar to Mozart. Now, if we change this, okay, for example, with an Indonesian song of children's song is Kakak, and we start to create generated music based on this new song, okay, without doing any programming. What will happen is the machine can run itself. And will generate a new program inside internally based on the data that we feed.
Hi,
This is
sorry to interrupt, Ardi. We couldn't hear the music that you generate, the artificial music. Is it possible to play it through your microphone?
Yes, yes. Again, I
think there's an option.
I see.
can you? This is the Mozart. Can you hear it?
I'm sorry, we can't hear it, but I'm very interested in this idea of artificial music, but maybe we can put a post to the link to this website so that our listeners
Okay,
can hear it for themselves.
I'll share the link. Okay, thank you. So, another example. Can you see my screen? Here, I will share my screen to this. Can you see it? So here is the example of data that we have. So we have transportation data, for example, with generated for bus, train, and car. to select for transportation mode. And when we train it, okay, and you see that this is like the glass box
No, I
inside.
can't.
You cannot see?
Okay. Oh, gosh. Okay.
Can you see it? So what is inside the program, you can see. And you basically know what is inside. And furthermore, the nice thing about this is you can also generate the inverse. Okay. So say you can predict with 100%, but you can also generate the inverse of what data actually produce that classes or category. Right.
Cardi, these are very, very interesting examples, but in my
Right.
role here as disciplinarian moderator, I think
Yes.
let's keep these in mind and move on a little bit
Let's
to
go.
the discussion.
Right. Let's come back to the discussion here.
Well, thank you guys.
Right. So the prospect for AI is that we will have a better and faster algorithm that can predict with better accuracy. But at the same time, closer relationship between the machine will create a trust and dependency to the machine itself.
Thank you so much. Thank you so much. Let me just, I'm just going to give us a really, really brief overview of Dmitry's work and his talk on AI on Monday, just so that we can kind of set the stage for a few things. So Dmitry gave a talk called What, Why, and How AI Can Transform Our Missions. Actually, I think it was AI. What, Why, and How Could It Transform Our Missions? It was a really interesting talk. So the thesis was that AI is going to revolutionize our lives and make the world more sustainable and equitable. This is, I'm just reading from the front slide. And that today's AI-based methods are nascent and narrowly applied, which means that we're just starting to attack problems that are very well defined, and who knows what the future will be. But already AI is integrating and impacting everything in science, from energy to health to climate to the examples that we've seen here of error correcting code, generating music, and locating earthquakes. So, AI, science and technology, they're something that we use to predict and inform decisions. And AI is becoming really, really part of this now. One of the things she said, Dmitry, that I thought was really interesting is that AI is not a thing or a technology. It's kind of a category of empowering ideas that are still nascent. And I find that that fits in really well with Stuart's description that an intelligent program, I know you said this much more eloquently than me, but an intelligent program is basically one that does what it's supposed to, that works. Then, Dmitry, you brought out the idea that AI, nobody actually owns the whole thing. They're all these little bits of AI running all over the world that have been built by many disparate teams of people, and yet there's no one sort of in charge, which I think goes contrary to a sort of popular idea that there's one, set of Darth Vader up there in the sky who's controlling all the AI that's coming down, but that's actually not true. It's distributed across the world. And then you said at one point, and this I thought was really revelatory, is that it takes a team to build an AI solution, and that team today is composed of people who pose problems, people who design solutions, coders who implement solutions, hardware people who generate the machines that the software is going to run on, and then all the little people who run around and build the pieces of the internet and maintain it and keep it going. And that at the end, we may have other people involved in these teams. For example, we may have ethicists and policymakers on there. And I have to say that, and the idea that the AI as it exists today is sort of fragile, which means that when it breaks, it just falls apart. Those two ideas were kind of new to me. And I would really like to, so you close with an idea that don't worry too much about knowing how AI works, because it's all evolving, but use it to think of the types of problems that you can try to solve so that you can sort of play your own bit in this big movement that seems to be happening around us. So I'd kind of like to start actually with asking you the question that came to mind during your talk, which was, if AI or whatever it is that AI actually is, that we're building these little bits and pieces of, if it's being built by teams all around the world and they're kind of plugging it up into a system that's bigger than all of this, is what we're building and what we're calling AI, is it really sort of a functional implementation of general human knowledge, sort of like a Wikipedia or a library that actually takes actions as opposed to just being a repository that people can go and look at and ask questions for themselves? Do you have any thoughts on that?
Thanks, Heidi. Yeah, thanks it's always interesting to see kind of the summary back and see, did I actually say what I think I was trying to say? So, again, thank you for that nice summary. Interesting talks before this too. It's more than a Wikipedia. It is going in a direction that I find much more interesting in terms of hypothesis generation. How you create understanding from data in ways you didn't think possible before. And then let me just give you an example. A few years ago, when I was working with the Cancer Moonshot back in 2016, we created a partnership to try and unlock data and push knowledge creation into drug discovery, nominally for cancer. And so we created a partnership with GlaxoSmithKline, with some of our national laboratories and the University of California, which is now it's in the Bay Area, the partnership. And we were able to unlock dark data that Glaxo had that they thought was not useful. So they had a lot of small molecules, 3 million of them, that never made it to drug trials. But where they had lots of data on how the molecules interact with tissue, with proteins, with animals and humans. But it was kind of just their dark data that they held around because it never went anywhere and they didn't deem it useful. And what we did is we partnered with them. We took that, we created active learning workflows. That means we took their data, we took computer simulations of chemical processes to fill in the gaps. And we plugged in also the opportunity for high throughput experiments. And we created a workflow to ask questions. Could we learn more from this data, filling in the gaps with simulation, and create some knowledge here or hypotheses we could test for new drugs? And so I had a slide on that during the talk, but I didn't talk to it because I ran a little long. So we asked 4 questions. So could we find different small molecules that had better manufacturability, that were less toxic, that had improved efficacy in treating a certain cancer, and better pharmacokinetics, so they worked in your body more effectively. And we put in a number of measures there. When we ran through the workflows, and in a matter of hours, was last year, we found 200 new molecules, chemically distinct from the 3 million already that were known, by Glaxo, distinct in the sense that the molecular structures had very low intersection in something called a Tanimoto distance. And so we found new molecules, new hypotheses that were better in all dimensions than all the molecules that have been known. And so it created new knowledge, something to test from data and simulations that no one had before. People were sitting on this stuff thinking it was kind of junk data or not useful, but we managed to pull out of it by creating these active workflows and filling in with modeling what the understanding was, what understanding was missing to create new hypotheses that could then be tested. It doesn't mean that all of these are going to be better, but you can generate something more than what you think you have in the parts by creating this kind of learning environment from the pieces.
I want to come back to this idea about hypothesis testing, because I think in a sense that's also what NetVisa does, right? It generates hypotheses that then analysts look at and decide if they're right or wrong. But before we do that, Tingobende, you said something that I think really applies here. In your talk, you said you talked about bankers who were sort of required to fake it and explain data that the computer came up with that wasn't actually something that a human would have found. And since this is really supposed to be a bit of a philosophical discussion, I wonder if you could elaborate a little bit on the fact that sometimes in computer modeling in general, or not even necessarily AI, we generate results that then humans may or may not be called upon to rationalize afterwards. Is that actually, is that a positive, a negative? Where does that fit in the scheme of your philosophical thoughts here?
I don't think we need to label it, because it's on the situations. If I'm in a self-driving car, and then the sensors capture a movement of I don't know, a deer on the road, and decides to brake. There is no need to explain anything here. You just may take the decision. But if you are in another setting, like in a bank, or I don't know, where you have a conversation between the system and a user, then yeah, you cannot just say go now, start now, you leave now for home, for example. If you look at Google Maps, for example, it tells you, leave now if you want to arrive home, at 7 p.m., for example. But you have some kind of explanations, because after that there will be some kind of traffic jam or something like this. In some cases, yes, to give explanations. In other cases, we might just want to action on the decisions that we make. That's what I want to say. For example, in the very, very nice example that Dmitry just gave, it's very, very, very interesting. In this case, these are new molecules that are discovered, right? I guess that it would be interesting to speeding up the test of these molecules, to be able to say that one of them might be useful for this kind of disease because it was discovered around other molecules that were targeting this kind of disease. Although they didn't work out, maybe this new molecule that was simulated is good. So it helps also to test. It helps guide the testing of these new data that were generated. That's what I was trying to say. Yeah.
I think that's really interesting, actually. This kind of works into Cardi's musical work here. So one of the things that I think is really interesting is you could imagine somebody taking the chord progressions that were coming out on the screen as you were generating it and playing it. I mean, there are lots of people who spend lots of time learning to play different progressions in the style of Rachmaninoff or in the style of Debussy. And you could imagine the music progressions coming out of a computer and somebody improvising on top of them, which isn't so different than the idea that we're coming up with suggestions for molecules and we're coming up with suggestions for fraud at banks. But in the end, I guess the question I'm asking, maybe Cardi, I'd love to hear your ideas on it. Is there going to be a point at which the relationship between the human as the final arbitrator and the machine as the proposer ends up getting flipped, and the machine is arbitrating and the humans are stuck in a position of rationalizing? Do you have a thought on that?
I think the job of human is actually to make decision. And in the near future, okay, when the machine will become closer to human, okay, then what is the job of human? Okay, at that point, the job of human is to create the decision. Actually, right now, we are actually dealing with many machines, right? For example, if you watch Netflix, okay, and you make decision to give rating, that kind of decision to give rating is actually the job of human.
This is
Right.
true.
Right. So when the machine can help us to do many things in our daily life, okay, then it is the job of human to make decision. Okay? At least the decision to say this is good or this is bad.
Yeah,
So
I think
Stuart,
that, I mean, I'd
yeah,
like to follow up on that. I think that ultimately this is where we humans have the ground truth, right? The machine can come up with a predictive model and says, you know, that this music is brilliant and wonderful and everyone should love it. But if we hate it, we hate it. And that's it, right? There's nothing the machine can do to persuade us that we're wrong to hate
Exactly.
the music or to hate the food that it
well now,
cooks up or whatever. And ultimately, I think this is where we often go wrong in designing the AI systems that we build, is that currently the only way we can build AI systems is that we have to specify the objective explicitly. And that's a very hard thing to do. Even for the self-driving car, the companies like Waymo they still have committees that are spending week after week after week trying to get the objective written down correctly, because they keep making mistakes, they keep leaving things out, they keep misunderstanding the interaction between the different terms in the objective function, and then the car behaves in some weird way, and then they go back and fix it. And the same thing happens in social media. If you try to optimize engagement or click-through, then what does the algorithm do? The algorithm learns to be manipulative, abusive, addictive, et cetera, causing all the social problems that we all know about. And in the long run, we have to change the way we build AI systems so that there is explicit uncertainty about the objective.
so I think that's really interesting. So Stuart, actually, I would love to follow up. So as part of preparation for this discussion, Ronan found your paper on the danger of killer robots, and the fact that maybe this could go on and be banned. And I think it fits well in this discussion. So in that paper, the statement was put forth that robots that are completely autonomous, that are told to go out and kill somebody by face recognition and operate off GPS and with no controls on them, can be very dangerous for maybe reasons that are sort of obvious. I'd love you to elaborate on that. So, I mean, I think the same thing could be true of a bot that is trained to give nasty comments into a Twitter feed. How in future are we going to deal with this?
Well, I think to some extent this is a little bit orthogonal, because I'm not so worried about an autonomous weapon that makes mistakes. I'm more worried actually about the fact that autonomous weapons, because they are autonomous, they don't need human supervision. That means that a human being can operate just as we do with bot armies, right? We can generate, millions of autonomous weapons carrying out mass attacks, just as we used to do with nuclear weapons, wiping out entire cities. We can now do that with autonomous weapons, without leaving a smoking crater and radioactive contamination for decades afterwards.
So is this the,
And if you think so, this is the reason why I've been writing articles about autonomous weapons. We don't need another class of weapons of mass destruction that's much easier to proliferate and much easier to use than a nuclear weapon.
so is this a is this a failure of objectives that are being correctly met by programmable things? Or is
I
it
would
a
say no,
failure
this
of
is much,
the
this
things
is much more
themselves?
about a failure of humans. I
Okay.
think that, you create this, it's the same reason we don't sell nuclear weapons in Walmart or on Amazon, is because there are people in the world who might use them when they shouldn't. And the same is going to be true for autonomous weapons. So I think it's really a failure of humans.
So
and,
does that mean the pocketbook nuke that I
yeah,
ordered
yeah.
last week isn't going to be a real one?
Probably not. I think you might want to get your money back.
Okay, Dmitry, I'd like your input on this a little bit. Is this something, so you're the person in this group that's closest to, I think, to policy making and decision making. Is this something that's talked about, the dangers of AI? One thing I forgot to say when I was talking about your talk was I really enjoyed the fact that it was very positive, but maybe there is a dark side here. Is this something that at DOE you're talking about, or actually, can you tell me if you're talking about it?
In terms of runaway technologies, it can go as far as we choose to do it. So, we are in control. And I think Stuart said it well, you can create and release these things if you want, but, it's a human decision in all of this, where to put it. The example of this already happening was, you see on Wall Street with the trading, the bots there that trigger on things, and they put in their projections and they buy and sell, and then we had that huge dip in 2018. And so things like this, are driven by external factors and the kinds of goals we have. We put these things, into their own as autonomous systems with some boundary constraints, and there can be downsides to it. So, I don't see yet the kind of the Pandora's box, if you will. I don't see it as suddenly we've stepped into this world where we can no longer control anything. I think there's still a lot of hard things that would have to happen before we automated things that were really critical to society. It's not a simple thing to do.
Let's pick up for a minute on this idea of hard things that have to happen. One thing that a message that I think is coming in very clear to me from everyone's discussion is that the current technology is sort of a set of ways of doing things that tend to solve very specific, well-defined program problems. Maybe, Teguende, maybe you can take this on. If there was something to happen in AI that would turn it into, we could call it maybe the Terminator AI or something like that, what would that thing have to be? Do you have any idea on that?
No, no. See, simply because I'm fully aligned with what Dmitry and Stuart already said. The main problem with AI will not be AI; it will be us.
I was actually thinking when I was reading up a little bit about your work in self bug fixing software. I was thinking, how the heck do I get my hands on some of this? But B, I was thinking so just when I'm writing code myself, I noticed that there's a suite of mistakes that I tend to make. Like number one is getting matrices backwards. And I was just wondering, in your work, have you discovered a suite of mistakes that humans tend to make that they are not aware of, that always need to get fixed?
Yes, it's called typos. It's like when you write text. You always make the same kind of mistakes. And actually, this is the foundation of our research. It's because AI is more about patterns, right? You try to get the patterns that you see. And if people are making the same kind of mistakes every time, this is the hypothesis of the research I'm doing. It's because people make the same kind of mistakes that are fixed the same way that I hope, that I can make an AI system that will learn to fix things automatically. That's the first thing. That's the easy part. The more difficult part is to be able to run to run the code, but the problem will be, what is the specification? Basically what Stuart called the ground truth. Even if I've never seen the mistake and I run the code, how do I?
Yeah, so that's quite interesting. I think this idea that there are, there's a whole suite of things that we're sort of trained to do, and then a suite of things that may exist that we don't know about, that we may catch this way. So Stuart, I thought there for a minute you might have gone swimming when you flipped off. But,
Sorry, my network failed, but it's back.
so actually, I'm going to come back to you, but for a minute here, Cardi, on this idea of things that we make all the time, and we can train an algorithm to fix. We had an early question on what it means when a AI has something included in a prior, and can an AI algorithm do or recognize things that were not necessarily included in the prior, in a prior, or not included in the framework of the program? And again, I'm thinking about your music example. One of the things that makes music enjoyable and listenable to is actually the mistakes. So the things that happen that are not in the harmonic lexicon that you're working in. Does that ever happen with your stuff, that you get some output that's really interesting, but that wasn't part of the original plan?
Yes. So basically, there are wide range of from the two extremes. Okay, one is the AI that can generalize, and the other extreme is the AI that actually kind of rote learning. So between these two extremes is actually continuous parameters. So yes.
Okay.
Yeah.
So Stuart, actually, you have a lot of insight on how you can, for example, find events that are not in the training set of the catalog, the earthquake catalog that you're looking at. What are the limits on that? Like, at what kind of new thing will not happen? And is there work done on sort of quantifying what that might be?
Yeah, so this is a really interesting question, and it applies to more or less any kind of AI system, is the extent to which contemplate
Stuart, oh, there, we got you back.
the extent to which it can contemplate events that are the kind of as you say, outside the prior. And for NetVisa, we simply add uniform around the Earth so that both man-made and natural seismic events could occur anywhere. And as we get more and more experience with natural seismicity, we can move a little bit of that prior into more geographically modulated. There's always going to be some residual possibility that a new event happens in some location that seismicity hasn't previously been observed. For example, I was sitting in my house in Birmingham, England, a few years ago, and there was like a 4.8 earthquake, and it's completely unheard of
Oh
to
my
have
gosh.
to have a perceptible earthquake in Britain. But you know, I had cups falling off shelves and things like that. Um, so it does happen, and you know, photographical priors is relatively easy to add a uniform. When you think about, for example, music, um, when people sing, they don't have to sing, you know, one note followed by another note by another note. Right? Human voice can do continuous modulation, right, which is not sort of a sort of non-digital kind of music, if you like. And so if your generative model says we're going to produce, you know, A followed by B flat followed by G, you can never generate continuously modulated frequencies because it's not in the vocabulary at all, right? So the question is, can you have generative models that are fully generative, that are universal, that allow for anything to happen, including, you know, continuously modulated notes, you know, sawtooth frequencies, you know, police sirens, you name it, right? You know, that could produce any physically possible sound. And the answer is yes. You can do that, and we know how to do that because Turing machines are universal or capable of generating any computable. You can put a prior that allows for any computable event to occur. It's just that if you do that, it's going to take longer to train your algorithm because it's so non.
Actually, let's so Stuart, you kind of broke out there again. Maybe Dmitry, you could take this up just a little bit. So, you know, we have this, I really liked your idea of fragility. And I wonder if that maybe, is this a crazy thing to say, that humans will remain the arbitrators until such time as machines lose their fragility? And this sort of ties back, I think, into what Stuart was saying, that, you know, humans have this sort of ability to deal with things in a continuous space, and when they wind up at a questionable situation, instead of just breaking, they just put two other things together and continue to go forward. Could you talk about that a little bit?
You know, I think we will put them into put AI more into systems, more dependency on it, not just as it gets less fragile, but as we find ways to get them to make our lives easier or meet the goals that we want. You know, I think they are tools that kind of extend the reach of what we can do by ourselves. And we turn to them, whether they're ready or not, to you know, become instruments to assist us in achieving those goals. You know, as we develop the internet and as e-commerce suddenly sprung up, without too much of a sense of where it was going or how central it would be to our lives, we never worried about security or the fragility of this and how all the things that could cause it to fail or make our lives more complicated on the back end. But you know, those will happen, and I think we've stepped into these kinds of technologies because we see the opportunities that they provide us in improving life in many different ways. And I will see that here. It might not be entirely break proof or idiot proof, as they say, but I think people will take the steps and it will get adopted.
There we have that happy optimism. Okay, we have a couple of audience questions coming in, but before we get to them, there's a question, another question for Stuart here. And this has been, I've been thinking about this for the last three weeks. So when we had our original planning session, you said that you thought that AI was going backward. And we've just had a wonderful, happy expression of how it's going forward from three other panelists. Can you please elaborate?
So in the early days of AI, there was very little focus on fundamental principles of reasoning, decision making, and so on. There was an eagerness to show that a computer could do X for any X, whether that meant passing IQ tests or picking up a block and putting it on another block. So people essentially hacked together code to achieve very specific tasks. And in most cases, that code was completely non-generalizable, very fragile, et cetera, et cetera. We called that the look, ma, no hands era, right?
Mhm.
Just like a little kid riding his bicycle saying, look, I can do this with no hands, but then usually they end up falling on their nose. And that happened with AI. It fell on its nose in the late 60s, again in the late 80s. And we learned a lesson that, in fact, you can do rigorous work on reasoning, on learning, on decision making. And we made a lot of progress from, I would say, the mid to late 80s through to 2010 or so on. And then people found this new toy, the deep network, and they're running around just like the little kids, say, oh, look what we can do with this, look what we can do with that. In most cases, they don't understand why it works, and they don't even understand if it works. So, for example, on ImageNet, which is sort of the big success, look, we can get very accurate classification of object categories from these images. It turns out that in many cases, the algorithm is not even looking at the object, right? It's recognizing what breed of dog it is by the carpet that it's sitting on, right? It's recognizing that this must be a parachute because there's a lot of sky in the image without even looking at the parachute at all. And those are the same kinds of mistakes that we made with neural nets back in the 70s, in the old, target recognition of tanks era, DARPA program. And so I think there's a lot of hype, just as there was in the 80s. There's a lot of over-optimism, over-claiming. And I worry that we will have a bubble that bursts, just as we did in the 80s. And I've, for several years now, I watch what's happening in self-driving cars. If those multi-billion-dollar investments fail to produce working vehicles that people can buy, then there's going to be a stampede for the exit. And I'm afraid to say that it's now 8 years since companies started claiming that they were going to be selling self-driving cars, this year or early next year. That was 8 years ago when those claims were made, and we're still waiting, and many companies have gone bust. Many companies have been found guilty of fraud. And people are maybe eyeing the exits. I wouldn't say they're running for the exits, but I think they are eyeing the exit because we're not seeing the progress that we should be seeing.
So as part of the oil and gas industry, I completely understand cyclic. So Cardi, what's your thoughts? Are we headed, is it possible we're headed for another AI winter such as we had before?
Yeah, I think I'm more optimistic than Stuart in this case. As I mentioned earlier, there are two extremes. Okay, one is the AI that actually learning by what we feed to them. The other side is actually AI that can generalize based on what is inside from the data itself. So in between, there are a lot of wide range parameter that is the part that creativity of the AI will come out of this. Right. So in itself, AI is actually a tools rather than something that we think as a personality. Okay? So when we talk about ethical or morality of the AI, it actually depends on the human being behind rather than the AI itself, right?
I wonder if that's not a problem, when the popular opinion sort of goes in a certain direction and people start to expect greater results than the research is actually producing. I think we see this. We see scientific crashes where the world is expecting something. And actually, before we get to the audience questions, I do have one more question that's kind of a lead-in from that, which is, who's responsible for communicating the limitations and the possibilities of AI clearly to the public? Because in this discussion, everybody here, I think, has a firm fix on what can be done and can't be done. So Dmitry, I'm going to give that one to you. Who's the person who needs to actually communicate this? What's our responsibility here?
That's a good question. I don't think there's a single answer to that because the kinds of tools that people apply to different domains, it's uneven. Some are more advanced and moving ahead, and others, it'll take a long time to get them implemented. So, there isn't a single voice for all of this. But, as I look at who is responsible, I typically gravitate to ask, the question a little differently. Who owns the risk? What is the operational risk in the sector where you're applying it? And if you're applying AI in some, robust or new way, and you should have a sense of what the risks are, and that if it is impacting people, it is your responsibility to try and convey how you assess those risks. But whether you're doing it to the grid, in a particular utility, or whether you're doing it for bank loans or job hiring, there are going to be different levels of risk depending on what your implementation actually is. And I would put the risk there and the responsibilities there, because there isn't a single answer to that question. I think it really depends on the details on how you've implemented and how it feeds into a decision process that impacts people somewhere in whatever domain that is.
Cardi, did you raise your hand? Did you have an idea there? Go ahead.
There is in terms of, for example, the self-driving car that Stuart was talking about. There are some progress actually to improve this self-driving car. So the only problem is actually, as Dmitry said, is the risk, right? So who is in case of accident, for example, who will be responsible for that kind of accident? Is it the car manufacturer or the owner of the car, or actually the government? That's the big question.
Maybe we're going to have a real AI when the AI program itself has to take legal responsibility for its actions.
Well, I think that's unlikely. At the moment, the car manufacturer is going to be responsible for accidents that are caused during fully autonomous driving. And I think that's what
they want to avoid, right?
I'm sorry.
Exactly what the car manufacturer, for example, like Toyota, want to avoid this kind of risk.
Right. But yeah, so they have to be able to afford it, and they're the only ones who can affect the degree of risk. The human owner cannot affect the risk caused by the car because they're not driving it anymore, right? So you always put the liability on the party that can reduce the risk, and it's going to pay for it. But the fact is that before we can sell a car to the general public to drive anywhere at any time, we have to go from where we are now, which let's call it 5 nines of reliability, to 8 nines of reliability. So we needed something that's 1,000 times more reliable than current vehicles. It's nice that they can drive during the daytime in Phoenix when it's not raining, and when there's nothing weird happening. but that's not the real world. Right?
Yeah.
So this is a really difficult task, and it needs common sense. We can't do it by training a black box from a bunch of training data.
Actually, there are two ideas there that I'd love to follow up on. So one is, Dmitry, when you were talking about the drug discovery, The Economist just this week ran a sort of what if scenario, and that would be what if an AI algorithm got the Nobel Prize for discovering some earth-shattering, life-saving drug. But it seems to me like we're happy to give AI the credit, but at the same time, we've just been discussing that the risk actually isn't in the program. So there's a funny little duality there. Let me, I've got some questions from the audience, although I would love to stay on this discussion for a long time. This one is for Tegwende, and it is, did the quality of the human side of processing interpretation, is it seen in a program's efficiency? In a case of failure, who should be responsible? So that brings us back to our idea of risk. Is it the machine or the programmer? I guess that's just what we've been discussing, but we'd love to have your input on it.
Okay, so let me go back first to say that I'm much more also optimistic than Stuart was, because all of the mistakes that we have today in AI are actually good mistakes. It's like a toddler, you learn, and then step by step we are going to run someday. And this example that you gave about not being able to detect the dog actually, but because we are detecting the carpet, that's actually a very interesting one, because actually the AI did its job. We just didn't feed it with the right data. So then I make the transition with the question that there are two kinds of mistakes in an AI system. There are the mistakes that we make in implementing the algorithm, and there are the mistakes that we make in the design related to the data. Like we have today the problems of ethics in AI. If you want to to give loans or I don't know what, and then you only use data of people from I don't know Santa Barbara, for example, then it's a very biased data. And if you take someone from I don't know from Brooklyn, you will never give him a loan simply because your training model is from Santa Barbara. This is a mistake, not the mistake of the AI. That's very important to distinguish. Yeah, it's a mistake. It's a mistake of the design. It's a mistake of the implementer. It's a mistake, but not of the AI algorithm. Sometimes the AI algorithm itself is also, mistaken because it's not comprehensive, because it doesn't infer very well. Sometimes the program that implements the algorithm is also buggy. So we have different layers of mistakes, and we will be able to draw out those mistakes by just trying. So the same for the car, as Stuart said, we run it and then we realize that we did not take into account one aspect. We do it again, we improve it over and over. But the car, because of the risk, the car manufacturer will always say, this is a fully autonomous car, but please keep your hands on the wheel. because it might not work.
Yeah, please keep your hands on the wheel. Of course, you could end up like the guy driving the train who has a little beep, beep, beep every 10 seconds to make sure he's still awake, and he learns to sleep through it. I've got another question here, which is we've kind of gone over, but so it's probably relevant to moderators' questions. Do all panelists think technological singularity is achievable? So I think what that means is that AI doing something outside of its model and I think I would further go, and this is just my interpretation, not the asker, but that would be to do something that's surprising and interesting. So that would be to come to a conclusion that's outside of the model that it's been given or the task that it's been given. Is this achievable? Let's see, we have here the GPT-3, which I don't know what that is, now can generate programming code. Is this an important step towards achieving outside of the box? So let's go ahead, maybe, and we'll just do a quick round robin on that. Why don't you start, Cardi? You're on the bottom of my screen, so we're going to go around that way.
Yes, thank you. So, technological singularity in terms of surprising and interesting, yes. But in terms of awareness, I don't think so.
Okay. All right, good. I like a short answer. Anyone got a dissenting opinion? Come on, Stuart, this is what you're good for.
Well, I mean, I agree with what Cardi just said. I think you know, AI systems have already come up with stuff outside the box. The technological singularity, right, is an approximation, right? It's this idea that some threshold will be crossed, and then once the machines cross that threshold, they'll basically self-improve so rapidly that they'll disappear off the charts, and the human race will be left far behind. This was called the intelligence explosion in a paper by Jack Good in 1965. So it's not a new idea. But it's not going to be like that, right? There isn't a single threshold of IQ that gets crossed. AI systems far exceed human capabilities in different directions, right? So for example, you know, the Google search engine in some ways has a far bigger memory than any human being, and can retrieve on lots of different cues, pictures, speech signals, music, text, and so on, you know, to a far greater extent than human can. You know, AlphaGo can play Go far better than we can. What's happening in AI is that we are gradually understanding how to broaden the capabilities, you know, so sort of think of these as long, narrow corridors, and we can gradually make those corridors wider so that the system is not just good at playing Go, but can actually play, you know, any kind of two-player game, and then any kind of multiplayer game, and then any kind of multiplayer game with partial information like poker. And as those corridors get wider, eventually the corridors start to join up, right? And then we start to get real generality where, you know, of the kind you might see in science fiction stories.
Okay.
But there's not going to be any one point where, you know, the machine IQ suddenly sort of, you know, exceeds the human IQ, and then it's off to the races. So it's going to be dumb in many ways for a long time, but superhuman capabilities, you know, as we're seeing in social media, you don't have to be a very intelligent machine learning algorithm to have a catastrophic effect on the world.
You don't even have to be a very intelligent person.
Well, that too, yeah. As we say, Hitler did it with words, and machine algorithms can do it with words too.
Well, okay, so following up in my position as evil moderator, I'm going to ask a follow-up question, and I'm not going to let you answer it. But before I do, the final thing that we're going to do at the end of this in about 2 minutes is we're going to go round robin and discuss the Turing statement, and I'll have Stuart remind us of what it is. So you're all forewarned and get a chance to think about it, except for you, Dmitry, who are going to have to think about the question I'm going to ask now, which is, so we have this idea that maybe there's going to be some tipping point. One of the things that I've been struck with, and this may just be my own ignorance, is that the algorithms and the machine learning, the actual ways of doing things, really hasn't changed spectacularly in the last, let's say, decade or more. What's changed is the ability to implement it. And there's a I listened to a very interesting dark web talk by Eric Weinstein, who's a physicist, who said that, you know, basically we're kind of running to the end of what just pure math that we know of can do. Is it possible that we are running to the end of the AI that we know it, of what it can do, but that there's some other idea out there that could actually just really change where we're at and actually push us to that tipping point? What's your thoughts?
Or you want this now or after the Turing question?
I want it now, and
Okay.
you have 30 seconds to answer this very simple question that I posed.
I don't see the end as simply as that. I think that we're going to see this get ever more complex. You know, these days, in the same way we built transistors, modeled it on solving equations, and we created the computer architectures over 7 decades that are tuned to solving models in certain ways. AI now is going to capture the algorithms. They're going to hardwire them. They're already doing it for convolutional neural networks and other things. You will find the relevant things being put down on the die into chips. And the most complex things today will be on a processor that does that. And now you can ask, well, what happens when you have 1 million of these? You know, if you take the most complex thing today and you create networks of these, and now you start blending simulation and data together into this kind of model, I think the world will explode in terms of the opportunity out there. I think we have to break away from just the data mentality, and down the road, it'll be the intersection of these that will have theory and experiment, data, simulation, fighting against each other, creating the paradigm that's coming.
Stuart, I see you nodding, but you don't get to reply. So we're going to do that. We're going to do the Turing roundtable. Stuart, can you remind us what the statement was? And then
I will try to put it up again, actually. Yep.
just read it. We've got 3 minutes left here, 4 minutes left.
Okay, so there's the statement. So I guess my answer is I think this could happen if we continue building the AI systems the way we build them, because we build them with fixed objectives. And if we create more and more powerful systems with the wrong objective, which we have been doing so far, then we end up basically playing a chess match, right? You're creating an opponent that has an objective that isn't aligned with yours. That's a chess match, and we know what happens.
Yeah,
So
that's really
we need
interesting.
to change the way we build AI systems to get away from this idea of fixed objectives.
Very interesting. Tegawende, what's your take on it?
We need to properly define what we mean by, machines will take control. Because if machine will take control means that machine will be so powerful that they can do a lot of damage, then yes. If we mean by machine will take control, if we mean by that the machines will have their own will, meaning that, without anybody giving them an objective, they will give themselves an objective, then I don't think so.
Okay, so a modified Stuart version there.
Yeah.
Cardi, what's your take? Cardi, we've lost you. Oh no, there you are.
Machine will take control in terms of better capability than human. That's yes. But with the related to the objective, actually we need to ask one question: who owns that machine? Who objective, right? So the one who take control is not the machine, because machine is just tool, right? So the one who owns the machine, the one who set the objective, is the one that actually set control, not the machine itself.
Again, I think we're coming into a question of objectives. So Dmitry, you get to close, but I also want you to so I would think that the machines taking control would mean that the machines had objectives of their own, and that would be them really taking control, as opposed to or maybe it's our own objectives that we messed up on. What do you think? Are the machines actually going to have their own objectives, or are they going to, is it always going to be a human-driven thing?
I could imagine, some kind of AI system that comes up with some objectives on, however, whether they're unique or not, hard to say that they would be. But, that's not hard to imagine. That's something more of an engineering problem, I would say. And you could imagine putting something into a critical system. You probably shouldn't, and you could say, well, what if we injected this and we released it a bit to feed on itself and come up with its own path? Sure, you could do something like that. It's not clear why you would want to, but it would be on you for doing something like that. I don't quite see the benefit of that, but in terms of being closer to how we think of humans, no, I think as Stuart said, we're a ways off from that world.
So the guns of August are not going to come to us through AI yet. Well, guys, it's 10 o'clock Pacific time, which I think means it's 7 o'clock Vienna time. And although I would just absolutely love to have a beautiful glass of sparkling Vienna wine after this conversation, I will not do so, seeing as it's 10 o'clock in the morning. But really, really want to thank everybody for your participation in this panel. I think it's been a really interesting discussion. And of course, thanks to the S&T for organizing. And thank you very much to Ronan. I believe our time is up, but nobody has cut us off. So maybe we have another 10 minutes that I didn't know about. Ronan, can you? Oh, here we go. Thank you, everyone. It was a lot of fun. Appreciate the meeting.
Yeah, our time is up indeed, and thank you very much. Thank you for all the panel members. Thank you, Heidi, for a wonderful job moderating this panel, and thank you also to the audience for listening in and putting in interesting questions. So yeah, that was a fascinating tour of horizon of AI and on the philosophical level. And thank you again for your participation. And next time, yes, we will have a glass of sparkling wine after this, hopefully.
Next time it's in person.
Things are, yes, hopefully if it's going to be in person.
Go out and enjoy evening in Vienna on my behalf. All right, thanks, guys. I think we're off air. So
Thanks, everybody.
Thank you.
Thank you.
Thank you, everyone.
I guess somebody else ends this. We just go.